There we go. Now we're going to do the party balloon. The party balloon, you got to have balloons to have this party. So we're going to do our party balloons. We got a little break, we got a little story. We're going to do our party balloon. What we're going to do is they're going to be perfectly spherical balloons. And for these perfectly spherical balloons, we're going to pump helium in them so they'll float at 5 cubic inches per second. That's probably a lot bigger than you can do, but we'll do 5 cubic inches per second. Okay? So we're going to pump it in there at 5 cubic inches per second. And what's going to happen, okay, when you take that first breath into the balloon, you notice how it pops out quite a bit, right? And then you take that second big breath, does it expand as much? No, because the air that you put in there the second time is filling in around another layer out here. So is that okay if I think about it like layers of air going out? So what's going to happen is even though you're putting it in at the same rate, it's not going to expand at the same rate. It's going to slow down as it expands. The rate of expansion is going to slow down. Is that okay?
Yes.
So, if I just simply ask you, what is the change in the radius with respect to time equals question when the radius is equal to 10 inches. Okay? Well, these problems are not that hard because you already know that you need the what formula? You need the what?
Circumference.
Area.
Volume.
Change in volume, you need a volume formula. Yeah, for change in volume, you need a volume formula. Who knows what the volume of a sphere is? It's okay, because you're going to know by the time you get out of here, you're going to fail. Ooh, it's actually 4/3 power cubed. That's the volume of a sphere, 4/3 power cubed. That's it, that's right. Okay? Now, what are you going to do next?
Take the derivative.
Do it. Take the derivative. Tell me what you get. Oh, pi is a constant. You don't need a product rule because everything's a constant in front. Yeah, you don't have to use a product rule because you just bring the 3 to the front, right?
Does that rather not use the product rule?
Yeah. So you don't need it because you only got one variable. Bring 3 to the front. Then once you get there, guess what? You just simply do what? Start doing what? Substitution. Do it. What's the change in volume?
If you have a 5.
Yes, ma'am.
Over there, if you bring the 3 to the front, how do you get 4?
What's 3 times 4/3?
4.
Flower child.
That's right.
5. Oh, whoever's watching the video won't know what we mean by that.
Oh, yeah.
Gosh, terrible. Poor people get left out because they just stay at home, don't come to school. That's right. Okay, that's 100, so you get 5 over 4, you get 1 over 80 pi. Now, I'm going to give you a little note here. See that pi? You make sure we know it's in the denominator. Okay? 1 over 80 pi inches per second. Equals dr over dt. Pretty cool. Yeah. See, these are nice because anytime it's a volume or an area or something like that, they're usually pretty easy because it's just a geometric formula that you already have. Now, the surface area is increasing. Would y'all agree with that?
Yes.
What is the change in surface area with respect to time equal when R is 10? You might need the what formula if you're going to talk about surface area? You're going to need the?
Surface area formula.
And what is the surface area of a sphere?
I don't know. Pi squared.
It's the area of a circle.
I know.
Surface area of a sphere.
What is it?
It's 4 pi r squared. 4 pi r squared is the surface area of a sphere. Now, I want you to know those in the future. I know today you probably never have been expected to know those, but from now on you're expected to know them. Everything is now fair game. Everything is fair game. Take the derivative of that with respect to time, and then just do substitution.
Yeah.
And there you go. Now, if you notice something, this is not true for any other three-dimensional shape. This does not work for any other three-dimensional shape. What I'm about to show you will help you memorize these formulas, but it does not work for any other three-dimensional shape. Look right here. Look right here. There's the volume, and look. There's the surface area. Some people say, oh, so if you take the derivative of the volume of something, you always get a surface area? No, just for a sphere. And there's probably a reason that happens. If you have a set amount of plastic and you put it in a cube, that's going to give you a pretty good volume. But guess what happens to the volume if you take that same amount of plastic and make it a sphere? Okay. Remember circles, if you take the perimeter of a circle, you have 100 feet of fence, and you make it into a circle, you will get the greatest area inside the circle. Okay, yeah, for a given perimeter, a circle gives you the best area. For a given surface area, if you have a given amount of plastic to use to make the surface, and you want to hold the most possible, make a sphere. All right? There used to be these things called party balls that they sold that were full of beer. Okay? And the reason they made them in spheres is because they were hoping they would sell real well. And for every sphere of beer they sold, they saved a lot of plastic. Fair enough? Does that make sense? So they were trying to save costs on the plastic. They didn't sell well. People didn't buy them. They didn't stay in the ice chest very well because they rolled around. They just didn't go over. But the beer companies really did try to start these party balls. And the whole idea was it would save them plastic if they made and sold enough. But there's our balloons for our party. Know your two formulas. Our balloon party.
So how do you find the answer for that?
Substitute in the R and the dr, just work it out. You know the R, right?
The DR would be what you got down there?
Yep. Yeah, that was kind of a step along the way. Yeah. Substitute those in and work it out. And then the next one is the party. Well, we got one more party to do.